In this video, we're going to be going over fluids in motion. First, we have to start off with what is the definition of a fluid. So a fluid includes liquids plus gases, and it is something that flows and takes the shape of its container. So for example, water is your classic liquid fluid, and also air is your classic gas fluid. So air behaves like a fluid, and that's why Bernoulli's principle is going to allow airplanes to lift. We have fluids in motion. So all fluids in this treatment are gonna exhibit a streamlined flow. So, for example, we have this object. It's kind of going to warp around it. And our fluid is heading in a direction, which is why we call it streamline flow. This is particularly the motion of a fluid in which every particle in the fluid follows the same path past a particular point as that followed by the previous particles. So this is our streamline flow, but what about turbulent flow? Our difference is that instead of continuing, it's going to warp. Now, what is flow rate? This is how much volume passes per time. Through a certain cross-sectioned area. So we would describe this as V is equal to AVT, or the quantity that changes in the volume over the change in time. We could write this as R is equal to area VT, T, and we would just say VA. So your rate of flow is equal to your velocity times your area. So let's say that you wanted to find the volume of this portion here, of this cylinder. So you have to find the area of that face. You want to find this, and you find VT. Your volume will equal to A times V times T. So your units are going to be in meters cubed over seconds. And for example, if you have a big pipe or a fast fluid, you're going to have a large flow rate. So for example, if you have a garden hose, it's going to be a large flow rate. And if you have a garden hose, if you have a fire hose, and if you have a garden hose, it's going to be a small flow rate. So your flow rate is dependent on both your velocity and your area. Now, what about when you have constant rate of flow? So for an incompressible, frictionless fluid, our velocity increases when your cross section decreases. So let's say that you have this pipe, and then in the beginning it's really large, but it becomes more narrow. So here it has a large cross-sectional area, and here it's smaller. So this portion has a volume of 1, this portion has a volume of 2. We'll call that area 2, and this is area 1. So our fluid will flow through. So R is equal to A1, V1 is equal to A2, V2. And this can be converted into an equivalent form of V1D1 squared, V2D2 squared. So this is called your continuity formula, or equation. What this says is that if area decreases, that means that velocity must increase because they are going to be inversely proportional. So for example, an application of this is if you put your thumb over your hose, that causes the water to speed up. So fluids speed up when squeezed through smaller spaces. So let's do a practice problem. Let's say we have a rubber hose and we have water coming out of it. So our water is flowing through a rubber hose, and its diameter, let's make this look more like a cylinder actually. So let's say that our diameter is equal to 2 centimeters, and let's say the velocity is equal to 4 meters per second. We want to find the diameter of the nozzle. So when the diameter is 2 centimeters, the velocity is going to be 4 centimeters, or 4 meters per second. So we want to find what the diameter is when the water is emerging at 16 meters per second. So we're going to use our equation that V1 D1 squared is equal to V2 D2 squared. So you see that the area is going to be proportional to the square of the diameter. So all you do is you're going to solve for D2 squared. And then you simply substitute in your values. V1 was 4 meters per second. D1 is 2 centimeters. And this is over 20 centimeters squared, which will give you 0.894 centimeters. So again, we have that when the diameter is 2 centimeters, you're going to have a velocity of 4 meters per second. Let's find when is the rate of flow for this. You're going to use R for rate of flow, which is equal to V1 A1 equal to V2 A2. So we know that A1 is equal to pi over D1 squared over 4. So we're going to take this, R1 is equal to V1, and we have our other equation, which is going to be R is equal to V1 A1. And because we have A1, we can substitute A1 into R. So if we do that, then we get the form R1 is equal to V1 times pi D1 squared over 4. Now we just solve for R1 by substituting what we have. So for V1, you have 4 meters per second. You have your pi, and then you have your diameter is centimeters. So in meters, that would be 0.02 meters squared divided by 4. That would give you 0.00126 meters cubed per second. And if it's meters cubed per second, we can also say R1 0.00126 m cubed per minute times 1 minute over 60 seconds, and then you would get 0.0754 m cubed per minute. So overall, when you have rate of flow, the steps that you should do and tactics that you should use include that you should read, draw, and label given information. Remember that your rate of flow, R, is equal to the volume per unit of time. Remember that when your cross-section changes, R is constant. Remember that R is equal to V1 A1 is equal to V2 A2. And also use consistent units for your area and velocity. In addition, since area of a pipe is proportional to diameter, a more useful equation would be V1 D1 squared is equal to V2 D2 squared. So we know that also you need to remember that the units of area, velocity, or diameter chosen for one section of a pipe must be consistent with those used for any other section of pipe. Now let's talk about the Venturi meter. So let's say that you have a setup with tubes like this. So it's about symmetrical like this. And this is going to be your measured height. This is going to be from where the water is. And we can draw the water flow like we've drawn earlier. So we're going to label this part A, and we're going to say water is coming in, and this part is C. This part is going to be B, water flows this direction. A key detail is the higher velocity in the constriction point. B causes a difference of pressure between our points A and B. So you can say PA minus PB is equal to rho GA. Let's look at some examples. So let's say you have blowing over paper. So if you're blowing over paper, piece of paper like this, and let's say this is a person, and they're blowing wind on the piece of paper. The air moves fast over the top. The pressure above decreases, and the pressure below is higher. So the paper lifts. Now, for another example, we have objects pulled together. So let's say you have two balloons like this. And we have a hose spraying water. So we have fast air between objects, and then that's going to create a low pressure region. So that makes, and then we have to remember that the outside pressure is higher. So that's gonna, the outside pressure is gonna push the objects inward. So the rule you need to remember is that if you have a higher fluid speed, that's gonna result in a lower pressure. That's because in Bernoulli, we have the pressure plus 1/2 rho v squared plus rho gh that's going to be constant. So that means that if V increases, that means that P must decrease in order to sum to the same thing. So faster flow means lower pressure. Now, let's talk about work in moving a volume of fluid. So this we're going to call to be P2. We're going to call this cross-sectional area A2. We're going to call this A1. And we're going to call this direction P1. We're going to label this as volume V. And this is also going to be volume V. So we're going to say that P2 is equal to F2 over A2. And also that F2 is equal to P2A2. Here, we're going to call this to be F1. That's going to be F1. And then here, we're going to say that this is going to be P1 is equal to F1 over A1. So F1 is equal to P1A1. Here we have a P1 flowing here. And then here we have A2. We have P2 here. And then F2. So we're going to call this horizontal, we're going to draw a line here. And then we can, from this height, we're going to call this to be H2. This is going to be, or just H. So right here. We're going to say the fluid is raised to a height H. So what we have is a chunk of our volume, which is volume V, moves through a pipe. And we have a change in area. We go from A1 to A2. And we have a change in height, which is raised by H. So on the left, we have F1 is equal to P1A1. So P1 is going to push the fluid forward. And then on the right side, we have P2. This is P2, and it's going to push the fluid backward. So this is your input. And this we call our output. So what we see is that pressure does work on the fluid to move it forward and lift it upward, which is a gain in gravitational potential energy. We can highlight this by looking at the volume. So this is volume V, and then up here, we're here. So our net work done on the fluid is the sum of work done by the input force F1 less the work, or we can say minus the work done by resisting force, which is F2 in the figure. So we can say our net work is equal to P1V minus P2V, which is equal to P1 minus P2 times V. So some other equations we can write for in and out is for in, let's actually move this here. So for in, we have these, and then for out, we have that. So that's fluid raised to a height h. We can leave that there. So for in, we have work in is equal to F1S1 is equal to P1 A1 S1. But A1 S1 is equal to V. Therefore, work in is equal to P1 V. And then work out, we're going to say work out is equal to P2 times V. So that's how we get our net work here. So what this means is that net work, it becomes kinetic energy change. So that means that the fluid speeds up or slows down. And that's how you get your gravitational potential energy change, which means that the fluid rises or falls. So this is why work is equal to P times V. So when you have high pressure, this means the fluid has more energy to push. And when you have low pressure, that means that the fluid has less energy. And if pressure ever drops, energy went into either speeding up the fluid or lifting the fluid. So we can also look at conservation of energy. So conservation of energy. So what we've seen so far is that pressure does work. P1 minus P2 times V. And that goes into kinetic energy and also gravitational potential energy. We know that work is equal to the change in energy. So we can write that energy change. We have delta K and delta U. Now we can apply the work energy theorem. We also know that net work is equal to this. So now you can set these equal to each other. So therefore we get that and now we can change this into Bernoulli. we know that rho is equal to m over v. So m over v is equal to rho. You can sub that in. So you get that P plus rho GH plus 1/2 rho V squared is going to be constant. So inside of this equation, we can actually break this up. So this part, P, is your pressure. And this P, this rho, this 1/2 rho V squared is going to be your motion. And then this is going to be your height. So, for example, your P is going to be the energy per volume per fluid pushing. Energy per volume from the fluid pushing. Your rho GH is your UG per volume, and your 1/2 rho V squared is going to be your kinetic energy per volume. So this is just energy conservation for fluids. So we are shifting between pressure, speed, and height. So if V increases, pressure is going to decrease if H is going to stay the same. If H increases, that means that P has to decrease or V must decrease. If pressure increases, then your V has to increase or your H has to increase. This is just work energy theorem, but applied to fluids. So pressure differences do work on fluid, and that work becomes changes in kinetic energy and gravitational potential energy, which is how we get Bernoulli's equation. So if you have a horizontal pipe, that means your height 1 is equal to your height 2. So that means that you have P1 minus P2 is equal to 1/2 rho V2 squared minus 1/2 rho V1 squared. And we know that the difference is delta P in delta pressure is rho GH. For a horizontal pipe, you can write the change in pressure is equal to rho GH, which is 1/2 rho V2 squared minus 1/2 rho V1 squared. That's because tubes sticking up measure your pressure difference. So your H tells you your pressure difference, and your pressure difference tells your delta V, your velocity change. So we have that from the equation P1 plus rho GH1 plus 1/2 rho V1 squared plus rho GH2 plus 1/2 rho V2 squared. We had this canceled out on both sides. So let's say we have an example. Let's say we have a setup like we did earlier with the Venturi meter. So in this Venturi meter, we're going to say that our V1 is going to equal to 4 meters per second. And we're going to say our V2 is this. Our height is 6 centimeters. And this height is just height. And this is our density. So we're going to start off with our Bernoulli's equation, which states that H1 is equal to H2. So the change in your pressure is equal to rho GH, which is equal to 1/2 of rho V2 squared minus 1/2 of rho V1 squared. So you can see you have rho on both sides, so you can just cancel that out. And you can clear the fractions. So then you have your GH 1/2 V2 2 minus V1 squared. So you can multiply both sides by 2. And then you just solve for your unknown speed. So V2 is equal to the root of V1 squared plus 2GH. So now we can plug in our values for V2. We're given that V1 was 4 plus 2 times 9.8 times 0.12. If you plug this in, you're going to get 4.28 meters per second. So the reason why density cancels is because you have your pressure difference. Because both rho GH and 1/2 rho V squared have rho, so it cancels. So that means that your delta V depends only on your height type, not your fluid type. So some things that I'm going to comment on here is that H does not mean your pipe height. H is the manometer fluid height difference. Also, faster fluid doesn't mean a higher pressure. That's because if you increase your velocity, that's going to actually decrease your pressure. And if your heights are equal, you always are going to drop rho GH. So when you have a horizontal Venturi tube, the pressure difference measured by H directly converts into changes in our fluid speed. We also have Bernoulli's theorem for fluids at rest. So this is just going to be basic hydrostatics when your fluid isn't moving. So we start with our full Bernoulli, which is this expression. So if the fluid is at rest, not moving, that means that your V1 is equal to V2 is equal to 0. So therefore our kinetic energy is gonna disappear. So we can cross out everything with a V in it. And what remains is gonna be that P1 plus rho GH1 plus, or is equal to P2 plus rho GH2. Rearrange that, that's P1 minus P2 is equal to rho GH2 minus H1. And you can just rewrite this as the change in pressure is equal to rho GH, or a change in H. So this is the pressure versus depth formula. Pressure versus depth. This says that pressure is going to increase as you increase your height. They're directly related. So that means that at a low point you're going to have a high pressure. And at a high point, you're going to have a low pressure. That's because the fluid pushes down due to weight. The fluid pushes down due to weight. So if you have a height like this where you're in water, and let's say you have a diver who is all the way down here, we can see that we have a change in height. And when the diver is deeper in the water, they're going to feel more pressure, and that change in height is the vertical depth distance. So we'll have to remember that this is the true form. It's not just pressure is equal to rho GH, it's the change in height. That is not just, it's not just H, it's the change in H. So we can talk about now Torricelli's theorem, or Torricelli's theorem. This is when you have no change in pressure. We're going to say that P1 is equal to P2. Delta P is equal to 0. So we're going to start off with P1, rho GH1 plus 1/2, rho V1 squared is equal to P2 plus rho GH2 plus 1/2, rho V2 squared. So let's consider a figure like this. That's going to be height. This is going to be height 1. And then this combined height, we're going to call height 2. So Torricelli's theorem states that V is equal to the root of 2GH. In this scenario, that P1 is equal to P2 and V1 is equal to V. So these conditions we can write over here. V1 is equal to V. We're going to say that P1 is equal to P2. Both points exposed to air. We're going to say that you have a large tank, so your surface area speed is equal to approximately 0. So we're going to say that V top is approximately going to be 0. And then we say that the fluid exits the hole. So we're going to say the speed is equal to V. So how did we get that V? We got this from rho GH is equal to 1/2 rho V squared. And we just get GH is equal to 1/2 V squared. And then we get this from multiplying both sides by 2 and taking the root of both sides. So what this means is that UG becomes kinetic energy and the fluid exits with same speed as an object falling from height h. So let's say that you have a cylinder like this. We have water coming out at different points, and this is a cylinder that's filled with water. So our velocity increases with the depth because of V is equal to the root of 2GH. So if you have a deeper hole, you have a bigger H, and you have a faster jet because they scale together. You also have the projectile motion effect. So we know that the water shoots out horizontally, then it falls. So the time in the air depends on the height from the ground, and the speed depends on the depth below the surface. So the maximum horizontal range is going to be from the middle hole. That's because at the top hole, this is going to be a long fall time, but slow speed. At the bottom hole, this is going to be a fast speed, but is going to be a short fall time. The middle is the best balance. So the holes equally spaced above and below the midpoint are going to land at the same horizontal distance. Pressure doesn't matter here. It cancels out, so only your height matters. And H is the depth below the surface, again, that determines the speed. And the height above the ground, it's going to determine the time in the air. So a fluid exits a hole with the same speed as if it had fallen from the fluid surface. So Bernoulli is going to turn it into a simple free fall.